Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, chapter 11. We're going to work on this example from the notes, page 7. Suppose a fire insurance company wants to relate the amount of fire damage in major residential fires to the distance between the residence and the nearest fire station. The study is to be conducted in a large suburb of a major city. A sample of 15 recent fires in the suburb is selected. The amount of damage, Y, in thousands of dollars, and the distance, X, in miles, between the fire and the nearest station are recorded for each fire. Assume that the linear regression model is appropriate. Some calculations are below. All right, so what I'm going to do is I'm going to use R to get all the information that we need to complete this problem. So the sum of the xi's is 49.2. The sum of the yi's 396.2. Sum of the xi squareds 196.16. The sum of the xi times yi 1470.65. And the sum of the y squareds 11,376.48. So I've saved all of those. And if I look back into the description of the problem, remember that there was a sample of 15 fires. So N is 15. So first, we're going to calculate the mean of X, 3.28, and the mean of Y, it's around $26,000. Okay, we get the sum of the X deviation squared and the sum of the Y deviation squared, the sum of the X deviations times the Y deviations. Our prediction line can be found by pasting in beta hat 0 and beta hat 1. And we calculate our beta hat 0 and 1 in the regular way for simple linear regression. And then we're going to paste in the prediction line. So we get y hat equals 10.2779 plus 4.9193x. So remember this 10.2779 is the y-intercept. So we would interpret that by saying a house that is 0 miles from the fire station on average will have about $10,277 of damage. All right, the slope is 4.9193. So on average, a 1 mile increase in distance away from the fire station is associated with a $4,919 increase in the predicted fire damage. Okay, so remember that we're estimating two parameters, the slope and the intercept. So k equals 2, and our degrees of freedom should equal n minus k. All right, so 15 minus 2, that leaves us with 13 degrees of freedom. All right, we calculate the sum of squared errors using the formula, and we can calculate S epsilon, the residual standard deviation. That tells us the typical distance from the data points to the line. So the typical distance is about 2.316. You could use the empirical rule and say that, 68% of the residuals are within one standard deviation of 2.31, and then 95, 99.7 for your empirical rule. Okay, so this next problem asks us to think about a house that is 3 miles away. So we can do this in two different ways. One is that we're going to calculate a confidence interval for the average damage of fires for houses that are 3 miles away, or we can calculate a prediction interval that says, what do you predict for a single house, what that fire damage will be? So in either case, we have to take this 3-mile distance away and calculate our y hat new. So we would predict that the fire damage was around $25,000 and some change. All right, so we can next get our critical value. We set our alpha level, since this is a 95% confidence interval, our alpha level is 0.05. Our critical value can be found using this QT function in R, right? We have to define our area in the tail. Since we have a confidence interval, we have 0.05 altogether, which puts 0.025 in each tail. We're setting our degrees of freedom to n minus k. The lower tail equals false because we want the critical value to be positive. So we get a critical value of 2.16. All right, we can calculate the standard error for the mean fire damage of many fires that were 3 miles away by using the formula in our notes. So our standard error is 0.6081. And from there, we can calculate our confidence interval, right? Our confidence interval is our point estimate plus or minus our margin of error. And in our case, our margin of error is equal to the critical value times the standard error. So we can get our confidence interval. So we get $23,722 up to $26,350. All right, interpreting the confidence interval in context of the problem. Okay, so the confidence interval is relating the average damage for many fires that were 3 miles away. All right, so we can say that we're 95% confident that the mean damage for many fires 3 miles away from the nearest fire station lies between $23,722 and $26,350. Okay, so next we can look at calculating the standard error for a single new fire. Okay, so this standard error should be larger than the confidence interval standard error that we're using. Okay, we get a value of 2.39. And now we can get a prediction interval. So remember, the prediction interval is slightly different than the confidence interval. The prediction interval is saying what is a likely interval for the fire damage for a single fire of a home that's 3 miles away. So it seems subtle, but if you think about the average damage for homes that are 3 miles away, you know, one home could have a lot of damage, another home could have less damage. So your confidence interval, the average damage is going to be less variable. But if we're just thinking about a single fire, there's more variability in a single fire than in a group of fires. So we calculate this prediction interval for a single fire, and we can end up saying that we're 95% confident that the damage for a single fire 3 miles away from the nearest fire station lies between $19,862 and $30,210. All right, I hope you learned something today, and I hope that you try to repeat this code. You don't have to do it from scratch, but make sure that you can understand each of the pieces, or if you'd like to, you can improve upon the code to make it make more sense for yourself.